Okay, let's talk about how we're going to quantitatively look at heat. I mentioned earlier that we would be using the units of joules, which is the metric or SI unit. Just like in our earlier unit when we were looking at kilojoules are going to be 1,000 joules. That's an important quantity or conversion to remember. I also mentioned that you might see the word calorie. In America, we often use this in food. So if you've looked at a food label before, you've seen calories. Though we'll talk in a minute about how that's different. But in chemistry, if we use calories, it'll be this lowercase c calories. And 1 calorie is actually equal to 4.18 joules. So what's bigger, a calorie or a joule? Well, a calorie is bigger, right? Because it takes 4-ish joules to make 1 calorie. It's kind of like it takes 4 quarters to make a dollar, so a dollar is worth more. A calorie is worth a little bit more than a joule. Even so, the calories on our food labels are these capital C calories. Take a look at something you have with you right now that has maybe a nutrition label on it. You'll see that the C is capitalized. I think they came up with this unit because if we use little c calories to measure our food, we would all freak out about the amount of calories we consume every day. Because 1 C calorie in food is 1,000 little c chemistry calories. So it's kind of like a kilocalorie, but we don't use the kilo prefix. So let's apply this. If we were going to convert 60.1 kilojoules to chemistry, little c calories, how could we use factor label to do that? Oh yeah, you thought we were done with that? It's back. Okay, so we need to remember our conversion factors. We know that 1 kilojoule is 1,000 joules, and 4.18 joules is 1 calorie. So we can use those two conversion factors to convert kilojoules to joules and then joules to calories. So we know that 1 kilojoule is 1,000 joules. So kj and kj cross out. And we've got joules now. So we have 4.18 joules and 1 calorie as our next conversion factor. And joules will cancel, and we will just have calories. So in your calculator, you'd type 60.1 times 1,000 divided by 4.18. And what I got was 14,378 calories. Let me double check that. I think that seems right. Now we need to round to sig figs, right? Because there's 3 sig figs here. Our answer should become 14,000, whoops, not 300 because there's a 7 after it, 400 calories. Now, what if we wanted to know why something heated up? For example, tonight for dinner I had some leftover pizza. It was from Domino's. First time I had Domino's in 5 years. I still personally prefer Papa John's. But I've got a piece of pizza. I'm going to put it on a plate, stick it in the microwave, and what's going to happen? Well, the pizza's definitely going to get warmer. But if I use one of these stoneware plates like what I have, the plate also gets pretty hot. Now, what if I used one of the Corel plates like what my mom has? This is kind of a thinner, different material. It actually isn't going to get as hot as my stone plate. Why is that? Well, it comes down to this idea of specific heat. Each substance has a unique specific heat, and that's basically, kind of in layman's term, going to tell you how quickly the rate at which that substance is going to absorb or release heat. How fast does it heat up and cool down? Or how much energy does it take to heat it up, to change its temperature? So the official definition of specific heat is the amount of energy needed to make 1 gram of a substance get 1 degree Celsius warmer. And the units that we use for specific heat are C. I don't know why. Maybe other letters were already taken. Maybe because there's a C at the end of specific. I don't know. But this is typically the letter that's used. Now your textbook actually uses the letter S for specific heat. You probably won't see that in any other chemistry course that you take later, and personally I prefer C, so that's what we're going to be using. Don't confuse C with calories though, because the units for specific heat are going to be more complex. Because it's the amount of energy, remember energy can either be calories or joules, needed to make 1 gram get 1 degree Celsius warmer, your units are going to be calories per gram times degrees Celsius, or joules per gram degrees Celsius. So either of those two units will work as your specific heat. And as I mentioned earlier, each substance has a unique specific heat, but there is one substance whose specific heat you need to memorize because we will be using it constantly. And that is the specific heat of water. Water has a specific heat of 1.000000 calories per gram degree Celsius. That's because they came up with the unit calories based on how much energy it took to heat 1 gram of water to make its temperature go up 1 degree Celsius. So it's exactly 1. Sig figs are infinite. It won't ever determine your sig figs. What if you wanted to use the number in joules? Well, 1 calorie is 4.18 joules, so the specific heat of water in joules per gram degree Celsius is 4.18. Good numbers to memorize. From your book, here's a table listing some common specific heat capacities. You don't need to memorize this or write it down, but just take a look. Do you see any trends about the things that have lower specific heat capacities? Well, all of these are, well, not carbon, but the rest of them are metals. Metals tend to have pretty low specific heat capacities, meaning that it doesn't take a lot of energy to change their temperature. If you've ever put aluminum foil into your oven, you know this. Aluminum heats up quickly, cools down quickly. On the other hand, if you use glass or some other substance, you might see that it takes a lot longer to heat up and cool down. If we were to do some quantitative calculations regarding heat, this is the equation that we'd want to use. Again, I think we probably ran out of letters because the symbol we use for heat is Q. And to find the heat associated with a certain process or reaction, you would take the mass of the substance, multiply it by the specific heat capacity of the substance, multiply that by the change in temperature of the substance. Remember that this delta symbol stands for change, and what we'll be finding is the change in temperature from the beginning to the end. So you'll do the final temperature minus the initial temperature. Again, your book uses the symbol S for specific heat capacity. I prefer C. Part of the reason I like it is because when I write this equation, without the time signs in there, you see Q equals mc delta T. And that delta kind of looks like an A. So I call this the MCAT equation. If any of you are aspiring doctors, this is the test you'll take to get into medical school. So that may help you remember the equation that we'll use here. Now let's take a thought experiment here for a second. If the temperature of something goes down, is heat going to be gained by that substance or released by that substance? Well, obviously its heat is being released, right? Because its temperature is decreasing. So what's going to be the value of our delta T? Well, if it's losing temperature, if its temperature is going down, it's going to have a negative delta T. So if this value is negative, then your Q value is going to turn out to be negative as well, right? So remember that, anytime that you release heat, which is exothermic, you're going to have a negative Q value. So just keep that in the back of your head. Always check your answer at the end to make sure that is consistent. Another important thing to notice when using this equation is what kind of units are going with each variable in our equation. This will be important because in problems you'll be given a whole bunch of numbers and you have to identify which number goes with which variable. The units for Q, for heat, are going to either be joules or calories or some version of that, capital C calories, kilocalories, kilojoules. The units for mass will obviously be grams. The units for specific heat capacity we mentioned earlier are either calories per gram degree Celsius or joules per gram degree Celsius. Whatever units you have on C will match the units you have on Q. So if you have joules in one, you'll have joules in the other. If you have calories in one, you'll have calories in the other. And the units on delta T will be degrees Celsius. You'll plug in Celsius here and Celsius here. Now you can also use Kelvin in both of them because the difference the difference in 1 degree Celsius is the same as the difference in 1 degree Kelvin. But primarily we'll see degrees Celsius for our temperature. Okay, I think we're ready to try a practice calculation, so let's dive right in here. In this example, we see that we've got 4 grams of glass, so grams is our mass. It is heated from 275 Kelvin to 312 Kelvin, so its temperature is going up. It's endothermic. It's going to have a positive Q value. Maybe right now we should find our delta T. How much does the temperature go up by? So we do 312 minus 275. That's going to be, let me bust out my calculator here, 25 plus 12, that's 37 degrees. Now notice that these are both in Kelvin, but we can still just find the difference in them to find our delta T. And it's going to absorb 32 joules of energy, that is our Q. And we're trying to find the specific heat capacity, C, of the glass. So we'll set up our equation, Q equals M times C times delta T. And at this point, you can drop your units out, but keep in mind that the joules are going to affect the units on our answer. So we've got 32 equals 4.0 times C times 37. And then we'll do 37 times 4, turns out to be 148 C, and that equals 32. So the value for our specific heat is going to be 32 divided by 148, which is 0.216216. Oh, that's kind of funny. And our units, since our Q is in joules, our units will be joules per gram degree Celsius. And let's see, we need to do some sig figging. This has 2, and our delta T has 2. So our final answer should have 2 sig figs. So that 6 will make the 1 round up to a 2. So it'll be 0.22 joules per gram degree Celsius, which is a reasonable specific heat capacity. It should be 1 or less for most substances. Okay, I've got another example here for you. What I'd like you to do is try this one on your own and finish it before you come to class. Make sure you write down your work in your notes. You've got 14.0 grams of water. Water. We know something specific about water. And the water is going to be cooled from 83.3 degrees Celsius down to 25.4 degrees Celsius. And I want you to calculate how much heat is associated with this process. Again, you need to be careful of the sign, positive or negative, on your answer. Okay, folks, that's all I've got for you right now. So I wish you a very happy MCATing.